In this module, the development of the numerical models to analyze the behavior of the composite plate shear walls and the concrete filled tube columns under fire loading is discussed. These models were used to perform parametric studies and understand the effect of various parameters on the fire resistance rating of composite plate shear walls and concrete filled tube columns. The obtained results were used to develop equations to estimate the fire resistance of the walls and the columns at the elevated temperatures. The results of the parametric studies are presented in Module 3 and Module 4 of the current presentation. This module covers the benchmark finite element models for both methods used on the wall section and the unit width of the wall. Also, a fiber-based model was developed in this study. This model involves three main steps, which are two-dimensional heat transfer analysis, section moment curvature analysis, and nonlinear column buckling analysis. This fiber-based model was validated based on the experimental and finite element analysis results. And also a graphical user interface was developed to allow the user better interaction with the fiber-based model. Three-dimensional thermal and stress finite element models were developed in Abacus. The developed models were based on sequentially coupled thermal and stress analysis within the finite element software. The temperatures of the nodes were obtained from the thermal analysis, and then the nodal temperatures were used as an input in the stress models. The model includes steel faceplate, concrete infill, tie bars, and shear studs as shown in this figure. Solid elements were used to simulate concrete infill. Shell elements were used for steel faceplates, and beam elements were used for shear studs and tie bars. The thermal and mechanical properties of the concrete and the steel material at elevated temperatures were applied according to Eurocode. The stress analysis was in two-step process. In the first step, an incremental axial compressive load was applied to the model. The magnitude of the load was increased from 0 to the maximum value in an hour. And in the second step, the axial load was maintained constant while the nodal temperatures obtained from the heat transfer analysis were applied to the model. To benchmark the finite element models, the measured surface temperatures were applied to the thermal model. On the left figure, the measured temperature 0 the wall thickness at 3-time instance for specimen CW1 as an example are compared with the obtained temperatures from the finite element analysis. The difference in the temperatures within the 0 to about 80 millimeter of the wall thickness is related to the moisture migration within the wall thickness. In the test, to pass the thermocouples 0, the steel faceplate, a small hole was provided in the faceplate. So during the fire test, water was escaping from the hole. So the water migration wasn't simulated in the models, and this caused a difference in the measured and estimated temperatures within the wall thickness at areas close to the hole in the faceplate. To obtain the obtained axial displacement from finite element analysis for CW1 are compared with the measured displacements. Figures on the right show the axial displacements against the time and the surface temperature. The specimen expanded for about 45 minutes and up to when the surface temperature reached about 450 degrees Celsius. However, due to degradation of the mechanical properties of the material at elevated temperatures, the wall began to contract after 45 minutes. Also, the comparison of the measured temperatures and axial displacements against time and the surface temperature for CW7 are shown in this slide. The finite element failure time is close to the experimental failure time. As shown in these two slides, there is a reasonable agreement between the measured axial displacements and the temperatures, and also with the obtained displacements from the developed finite element models. Composite plate shear walls for buildings typically have width significantly more than the wall thickness. So the walls can be subjected to fire from two sides or just one side in cases where the wall may be designed as a fire barrier. Also, composite plate shear walls may be designed with different configurations like planar walls or C-shaped walls. The interior region can be conservatively modeled as a unit width wall with the width equal to the tie-bar spacing, representing the whole wall, because the regions of the wall closer to the boundary elements may have higher axial compression strength and stiffness than the interior regions. A schematic distribution of critical axial compression capacity of C-shaped composite plate shear wall is shown in this figure on the right side. This axial critical load distribution can be verified by comparing the axial load distribution in different regions of a wall during exposure to fire loading. The cross-section of the simulated wall with boundary elements was divided into three regions along the width, which would have one middle region and two ends. In the finite element model, a rigid constraint was applied to the top surface of the wall. The axial load was uniformly applied along the width of the wall. The normalized axial load of the concrete infill and faceplate in the middle and the end regions are compared in the figure on the left. The axial reactions were almost the same at ambient temperature for both regions. At the beginning of the analysis, the model underwent thermal expansion, and the axial force in the concrete field dropped, and most of the applied load was transferred to the faceplate. But after about 40 minutes, due to the reduction of stiffness and local buckling of faceplate at elevated temperatures, the applied axial load was transferred to the concrete infill. The summation of the base reaction forces in the middle region was lower than the end regions, zero at the fire exposure. So, a unit width wall taking from the interior region of the wall can be used to conservatively estimate the strength of the wall at elevated temperatures. The developed finite element models for unit width wall is shown here on the left. The width of the model was equal to the tie bar spacing, and the faceplate was modeled on two sides of the wall. The fire loading was applied to two sides, assuming that the heat flow is perpendicular to the width of the wall. Symmetric boundary conditions were applied to edges of the faceplate, and the transitional degrees of freedom along the wall width was not restrained to allow the column to expand along its width at elevated temperatures. The axial displacements of the unit width wall models is compared with the modeled walls with whole section, and also the experimental data in the figures on the right. The unit width wall models gave comparable results to the wall models and the experimental results. The failure time for unit width models are lower than those for experimental data and wall section models. The failure time of the SCW4, the figure on the top, was about 155 minutes, which was reduced to 139 minutes for the unit width wall models. The simulated unit width walls have a lower axial capacity, as it was discussed in the previous slide. However, the general behavior is in good agreement with the experimental behavior. So the unit width wall method can be used to conservatively analyze and design composite plate shear walls with different configurations and dimensions. In addition to finite element models, a two-dimensional fiber-based numerical model was developed to simulate the behavior of composite axial members, including composite plate shear walls and concrete field tube columns under fire loading. The main goal in developing this model was to provide a time-efficient and accurate tool that could be used for parametric studies and also for design of composite members under fire loading. The two-dimensional fiber model is a section-based model which is based on analyzing a section of the column or wall. For the analysis, the cross-section is divided into fibers consisting of nodes and elements. A discretized section into fibers is shown here. This figure shows a cross-section of a concrete field tube column with steel and concrete elements. This model can be used for square and rectangular concrete field tube columns and composite plate shear wall systems. Standard fire curves or user input time temperature curves can be applied, and also a layer of fire protection can be simulated around the section. The MATLAB software was used as a platform to develop the tool, and also a user interface was developed and implemented to allow straightforward interaction of the user and with the software, which will be presented at the end of the current module. This fiber analysis is an incremental analysis where the results of each time step will be used for the next time step. At each time step, the procedure can be divided into three steps, which are two-dimensional heat transfer analysis, section moment curvature analysis, and nonlinear column buckling analysis. These steps will be discussed in the next few slides. The first step in fiber-based analysis is a two-dimensional heat transfer analysis, where the The temperature of each node and element of the section is calculated based on the thermal properties of the elements. Heat can be transferred in three different ways, which are conduction, convection, and radiation. Conduction is the transmission of heat between two solid objects which are in contact. Convection is the transmission of heat between a solid object and the moving fluid which are in contact with each other. And finally, radiation is the heat transfer between two objects in the form of electromagnetic waves. The heat balance equations which between objects can be set up by considering all the heat transfer types. These equations in their finite difference form can be solved numerically. The first step of this heat transfer analysis is calculating the surface temperatures, which are assumed constant along the height of the member. So the calculated section temperatures are true for entire section. A flowchart of the thermal analysis algorithm is shown on the right for each step. At every step, the thermal material properties of each element is calculated based on the temperature of the element. Then the surface temperature of the section is calculated based on the gas temperature. If the surface temperature is specified by the user, this step can be skipped. After obtaining the surface temperatures, the element's temperature can be calculated based on the thermal inertia and the heat flow for the elements. This figure is showing an example of thermal analysis results for the calculated element's temperature. This section was heated from four sides. There is a thermal gradient in the cross section where the temperature of the elements closer to the exterior face is higher than the middle of the section. The exterior element's temperature is around 800 degrees Celsius, while the temperature at the middle of the section is less than 100 degrees Celsius. The next step of the analysis involves generating a moment curvature relation for the section at its current temperature and axial load. A flowchart showing the algorithm to get the moment curvature curves is shown here. The curvature is increased in small increments. The section moment for each curvature value is calculated using an iterative process. An initial centroidal strain is assumed and its value adjusted based on section equilibrium. Element total strains are calculated from curvature and centroidal strain based on the plane section assumption. Thermal strain is also calculated for each fiber from its coefficient of thermal expansion and temperature change. The mechanical strains are then obtained by subtracting thermal strains from the total strain, which are provided as input to the material stress-strain temperature curves to get stresses in the elements. Once the force equilibrium is established, net moment of the section is calculated by summing up the moment contribution for each element. This figure shows the moment curvature diagram for a section at ambient temperature, at failure, and at a specified surface temperature. The obtained moment curvature plot is then used in column buckling analysis, which is discussed in the next slide. The members, like columns or walls, are discretized into several stations along the height. Up to here, we have calculated the element's temperature in the cross section and created moment curvature diagrams in the last two steps for the stations along the height of the members. In the third step, Newmark's inelastic buckling analysis was used to calculate the deformed shape of the members. A flowchart of overall inelastic buckling analysis algorithm is discussed in this slide. The calculated moment curvatures were used to obtain curvatures at various stations along the height of the member. An updated deflected shape is then calculated uh, by numerical double integration of the curvatures. This shape is compared to the assumed shape at the beginning of the time step, and the iterations were carried out until a convergence is achieved. If the station's moment along the member's height exceeds the maximum moment that can be developed in the section, the column will fail in global elastic buckling. If the axial force equilibrium cannot be established at any step while generating the moment curvature plot, the member would fail in yielding or crushing. Moving over to validation, the model was validated by comparing the obtained results from the model to the experimental data and finite element results for composite plate shear walls and concrete field tube columns. This slide shows the temperature variation of a steel node for wall specimen heated on three sites. This slide compares the obtained temperature profile, zero the wall thickness, from the fiber model and finite element models at 30 minutes and 4 hours of heating. The obtained temperatures from the fiber-based heat transfer analysis are in a good agreement with finite element results and measured temperatures experimentally. In this slide, the axial displacements obtained from the model is compared with the measured displacements in a fire test of concrete field tube column. The column expanded until the surface temperature achieved about 550 degrees Celsius, and it followed by the contraction of the column due to the degradation of the material stiffness at elevated temperatures. For further comparison, the axial displacement curves obtained from the fiber model and finite element models were also compared for composite plate shear walls. The slide shows the plots for axial displacements versus time. It's evident from the graphs that there is a reasonable agreement with the obtained results in the finite element models and the fiber-based model. The position of the peak axial displacements matches in the fiber model and the finite element and the obtained results from the finite element models. The discrepancies can be explained by simplifying assumption made in the fiber model. Before finishing this module, I would like to show the developed interface for the fiber-based tool. A user interface was also developed to allow an easy interaction of the user with the developed fiber-based tool. This slide shows the preprocessor or input window for the developed graphical user input for the tool. The user can enter the geometric properties like width and the depth of the column, the strength and stiffness material properties, and the amount of the applied axial load. the load can be specified as a fraction of the nominal capacity of the section at ambient temperatures. There is also an advanced option tab to modify more properties such as fire protection material properties. In the advanced option, we can select the material stress strain curve and the heating case curves like using ASTM E9119 standard time temperature curve or user input time temperature curves. When all the inputs are provided, we can click on the Submit Input button to run the program. When the analyses are completed, in the box on the bottom left side of the window, we will have the key output parameters such as the time to failure and the maximum surface temperature at the failure. We can check the detailed results such as the element's temperature, stress and strain within the cross section, and the axial displacement of the column or the wall by just clicking on the desired parameter on the bottom right box. In the next slide, examples of the temperature and stress outputs within the cross section are shown. There are different options to check the temperatures within the cross section of the wall or the concrete filled tube column. For example, the left figure shows a two-dimensional temperature distribution within the cross section for a composite filled tube column at 25 minutes, where the temperatures around the cross section are about 700 degrees Celsius, while the temperature is about 20 degrees Celsius in the middle of the cross section. The right figure, the temperature of the elements is shown respect to the time and the width of the cross section. The temperature increase rate of the elements close to the surface, like at x equal to 0, is higher than the increase rate of the temperature for the elements in the middle of the section. The axial displacements of a wall or column against time or surface temperatures can be obtained from the tool. For example, the axial displacement results for a concrete filled tube column are shown in the figures on the left. The results show that the column had expanded up to 12 minutes, or when the surface temperature reached to about 550 degrees Celsius. And then the axial displacement decreased when the temperature in the faceplate exceeded 550 degrees Celsius. The axial displacement drop followed by a slight thermal expansion of the concrete infill until the column lost its load-bearing capacity. The figures on the right show the generated stresses within the cross-section at two time steps. As it can be seen in the figures, due to the thermal expansion of the steel faceplate, the stresses in the faceplate around the section are more than 25 megapascal at 12 minutes. However, at 30 minutes, due to the degradation of the mechanical properties of the material at elevated temperatures, the stresses in the faceplate had reduced while the stresses in the concrete elements were increasing.